Hey, Alodeep, thank you for coming in. You're a noted Indian American computer scientist. You're co-founder and CEO of LifePlus. You've had a remarkable career, including in the semiconductor industry, for example, Intel Corporation, and so on. So thank you for coming in and sharing so many of your insights with our audience.
Stephen, thank you very much for having me, and I really appreciate and feel honored to be appearing on your interviews. Really appreciate.
So my audience tends to be actually CEOs, board members, co-founders, and founders. In fact, it always tends to be those are the top three positions. Then I have like engineers and professors and students and so on. But everyone is always interested, and that is, what are those inflection points in your life that made this wonderful career you have today, or created this wonderful person you are today?
That's a very interesting question indeed. So, thinking about the inflection points, the first inflection point or the moment that comes to my mind is when I was in high school and we were in a physical science class, and we had a high school teacher that we all very liked him. I mean, because he used to surprise us almost in every class, showing something new. And one day he walked into the class with a small, teeny chip in his hand. And that was the first time the entire class, a class of 40 students, saw an electronic chip physically. And mind you, this was in the mid of 1990s. So, the students, high school students, were not very familiar with chips and motherboards and those kind of stuff yet, and especially in India. So he showed that chip and he said that almost all complex mathematics that you guys have learned so far and even beyond, this little thing can compute them not even in seconds, in milliseconds. So even before you blink your eyes, it will give you the results. That was really an inflection moment in my life. I thought that, and then I still vividly remember his next comment. He said that we all worship God, but think about the people who built it. Won't you think that they are almost close to God? Because they could innovate and build such a teeny physical object that can do such a humongous amount of mathematical computation within like a even before a blink of an eye. And then I started feeling like, man, I have to get into this space, try to get close to those people who have invented this and who have done such a miraculous thing. And then, over the time, over the next years, as I graduated from high school, got into the engineering program, got into computer science, slowly I got kind of aligned myself in that path, and eventually, landed into a company that is considered one of the founding fathers of the semiconductor world, the Intel Corporation. So that was one inflection moment. The second inflection moment came when I was at Synopsys, and this was a personal moment actually. So I already completed my studies. I was working at Synopsys, which is also a very deeply aligned electronic design automation company. And so what happened is very personal. My grandma was particularly sick in India, and she was not sick because of any debilitating illness like cancer or anything. She had asthma primarily and few kind of blood parameters up and down. But what was happening is she was going back and forth hospital and home in 2012. And my dad's are three brothers. My youngest uncle is a cardiologist who used to practice in New York that time. Now he is in Florida. He and I had multiple conversations, and he was in a great dilemma whether he should go back every time when she was hospitalized, which was not absolutely possible given the job that he had in hand. At the same time, he was feeling like I don't have the information, the basic information that I can effectively communicate with my friends and colleagues and counterparts in India who are taking care of my grandma. So that led me thinking that I'm quite sure the biosensors have advanced to a point that we can easily monitor multiple of these core biomarkers in real time and send it to the internet layer. Then anyone anywhere can access that data. And that can tremendously, you know, uh, expand the scope of medical treatment for people from every corner of the world. So I started looking into this problem. What are the sensors available? I slowly started speaking with few people. I found another guy, again an electronic engineer from Broadcom. So we got a good alignment. Then I also found one of my PhD days buddies. He was teaching at University of Maryland. He also started a lab in University of Maryland on advanced biosensing and smart sensing. So I spoke with him. He was also interested in joining this effort. Then we found another doctor who did his undergrad in electrical engineering from Northwestern. So he's a doctor engineer that way. So we formed a small clique, a group of 4 or 5 people, and we started looking into different sensors. Eventually landed into the optical sensor that we'll talk about. So that was another inflection moment, that how can technologies really aid the advancement of treatment of people at every corner of the world, and make it very simple and make it accessible, affordable to every doctor in the other parts of the world. So these were the two moments that I could recount.
So let me reflect on what you're saying then. In high school, you had a teacher, and this teacher actually showed you a semiconductor chip. And that teacher gave this narrative that this chip could do amazing computations and in a fraction of a second, and something that would take much longer for a human being to do. And that was a defining moment for you. And actually that resonates with me too, because I used to work hard wiring logic, and then worked with vacuum tubes and then transistors. And then those became chips, because you could hand wire gates into different logic circuits and combine them. And then of course you got into integrated circuits, where you had a combination of these and could have much more complexity. So I understand that history.
Mm.
So I can see how that could be a defining moment for you. And then you end up working at Intel, which really is the sort of the flagship corporation for taking transistors into integrated circuits, into large scale integration, and then into CMOS circuits, and also into processors, right? From some of the early 8080A processors to other processors, to the ones you see today, which are combining billions and billions of elements onto a chip. And then so that experience then led you to realize, when you had a family member with this health history, and saying, you know what, maybe we can do something with sensors, and sensors are based on these chip technologies. And that led you to say, you know what, maybe I can start a company in this area, and working with colleagues who have this kind of background you have of interest in semiconductor technology. And as you mentioned, one of your colleagues has a medical and engineering background. So I can see this journey of then getting into translational science. And what I mean by that is something that's very practical. So so you left Intel, and after you worked with these other companies, like how long ago did you decide to then start this company called LifePlus?
Before answering that question, I wanted to tell you a couple of goosebump moments I had at Intel. My office was in the Robert Noyce building, the headquarter building in Santa Clara, and I was fortunate enough to walk into Gordon Moore's office one day. And Intel doesn't preserve any of their past CEOs' offices except Gordon Moore's. They have preserved that office, and you would immediately get a goosebump if you walk into that office. It's an open office. There's no closed door. Intel doesn't have a closed door system at all, and you know that very well. Gordon's is also an open office, but you can literally see that all those fabs, those milestone processors are all lying on that wall, and literally one desk where he used to sit and define the defining moments of the journey of semiconductors. You literally get a goosebump. The next one I got is right at the main door of the R&B building, the Robert Noyce building. I was walking out. I saw a very senior old gentleman with his wife coming in, and he was kind of literally, making his way, slowly walking. In a second, I realized it was Andy Grove. And I shook my hand with him, and I almost felt like this is the touch of God that I got inspired when my high school teacher said, "Don't you think the guys who built this chip is almost close to God?" This was probably the very closest I could get to the real sense and touch of God. And that was another defining moment in my life, that I was so fortunate that I could experience these two moments. So now, getting to your question on, I think you were asking that what are the other companies that I worked on. Fortunately or unfortunately, I didn't work on too many companies before starting my own company full time. My career started at Synopsys. I was part of Synopsys's test automation R&D staff, and then I switched to Intel. And at Intel, I was in various groups. My last stint where I left was I was one of the four architects of the Intel's first AI processor. Um, and by that time, my own venture became so demanding that I had a kind of private conversation with my wife that what should I do, because I couldn't really keep my 2 feet on two different boats. I had to choose one, and I kind of reluctantly, grudgingly, eventually, also with a lot of excitement, chose the boat that I'm in right now. So I only worked in for Synopsys and Intel before doing LifePlus full time.
And then, so that's really, really fascinating. To be inspired by two iconic pioneering figures in the chip and semiconductor industry is quite remarkable. I guess, and that legacy continues even with people like John Hennessy, who's
Yes,
now chair of Alphabet, right? And creating this RISC architecture, rather from CISC, to sort of reduce instruction set kind
yes,
of way of thinking. So again, simply remarkable. And what maybe the audience doesn't realize is that semiconductors are actually the foundation of everything. Everything is really built on
exactly,
semiconductors.
exactly, exactly. People sometimes get too fascinated with the algorithms and its vast applications, but nothing would have been possible if the backbone semiconductors did not progress to this level that we have today.
And the fact that you worked then on embedding AI kind of capability within chips, and that's deep acceleration and deep learning came because of GPUs. Now, NVIDIA has been the beneficiary of that
Yes.
to a large extent, but and now other companies are involved, even Microsoft and Google and others, and AMD and Intel, of course, they've doubled down IBM and so on, but really NVIDIA has been
Pioneer.
the beneficiary. So you had your feet in two camps, right? You were in the sort of the fortune company camp, and then you started this company called LifePlus, and you had to make a choice. Now, tell me, what is LifePlus? You're the CEO and founder of LifePlus, or
Right.
co-founder of LifePlus. What is LifePlus?
In one single word, Life Plus is the focus of Life Plus is to build a platform for every individual who is or has suffered from a chronic illness like diabetes or hypertension or any cardiovascular disease or respiratory disease. A lot of burden is on you. You are always worried that, am I managing my condition well? This is not a condition that you will die tomorrow, but say still, I mean, it's a big problem. You have to take medications, you have to manage multiple things, otherwise you will be on a downward path. So this burden we really want to eliminate from people's hand and people's mind. The way it should work is you wear a simple wearable device like I'm wearing this watch, and this device will track your glucose, your blood pressure, your heart rate, heart rhythm, respiration, oxygen saturation continuously without any involvement from you. And this data will go to your mobile app, and then it will go to your cloud. And from cloud in real time, we are sending it to the clinics. So your loved ones can see your data in real time. Remember, that was my primary objective with my grandma's illness, that I wanted to track her primary vitals in real time, sitting in New York when she was in India. So that problem has been addressed, that we can look into the data in real time, sitting anywhere. It could be the loved ones, it could be the caregivers, it could be your clinic. So as a person suffering from a chronic disease, you don't need to worry about it. You are completely covered. Our goal is to give you the peace of mind that is completely missing. So that is basically the fundamental objective behind building a product and a platform that will track your primary biomarkers continuously, non-invasively, without any user involvement, and share the data in real time with your audience.
So, biomedical innovation is an interest of mine. And in fact, I sit on the leadership board of a group called the Tarasak Institute for Biomedical Innovation. So, and I've always had an early interest in sensing devices and chip technology. And so I can see the value of what you're doing. And then I guess the question is, how does it compare against when you do other means or more the traditional means of glucose monitoring and blood pressure and heart rate and some of the other things that you're monitoring? How does it compare against those existing traditional techniques? And the other thing is and the second question is, I've got a Ultra from Apple, and it does a lot. How do you compete? And for example, it does heart rate and all of these other things. It doesn't do glucose or blood pressure, but no doubt they're working on it. So how do you compete against people like Apple?
So I think you had two questions. One is more on your first question was more on, if I remember it correctly. Sorry, can you please repeat your first question? Second question is against Apple, and that's a marketing business question that I will answer. But what was the first question, Stephen?
Yeah, how accurate is your?
Oh, yes, the accuracy. Yes, so that's a great question, and that's where we wanted to show our sincerity from the get-go. And that's one of the differentiation against all sorts of different wearable devices that you see in the market. And many come with many tall claims, but what they really lack is substantial clinical data backing. So first thing, because we had a doctor in our team from the beginning, we decided we're going to go the path. By the way, this is not a consumer tech. This is not a consumer device. We designed it from the get-go to be a medical device, but we wanted to make it look like a very socially acceptable looking medical device, not a clunky kind of medical device that we all have seen too many times. We wanted to make it a socially acceptable looking medical device, but what we wanted is partner with the topmost clinical research organizations. Like we partner with Mayo Clinic, we partner with Stanford, we partner with Cleveland Clinic. We did many clinical studies, IRB control studies, collected data against the traditional medical devices like a Abbott or Dexcom continuous glucose monitor, or finger stick glucose monitor from Roche or LifeScan, or or a blood pressure cuff like Omron. So we compared against this. So we did a 66 subject diabetic subject study against Dexcom's continuous monitor in a metabolic research institute in San Diego. We did 3 clinical studies on inpatients, one in Cleveland Clinic, Abu Dhabi, one in India, and another one in Malaysia with the government hospital. And we collected a lot of data against fingerstick, more than 500 patients, admitted patients, against fingerstick, against cuff, against oximeter, all these parameters. So then we analyzed this data. So we used part of the data in training our model and use the other part in validating and reporting the accuracy. So we are right now, for the glucose, we are within 15% of the CGM or the finger stick. For the blood pressure, systolic and diastolic both, we are within 10% of the cuff. And I wanted to bring in another flavor to the accuracy matrix in this context, is that the blood pressure cuff or finger stick glucometer, they are discrete data point devices. So they have certain accuracy expectations. You are not going to prick multiple times. You're going to prick probably 1 or 2 times a day at most. Whereas we are collecting data continuously. So the power of statistics, the power of volume will come into picture. So we can afford to be slightly deviated from the gold standard, but still attain our goal because of the power of longitudinality of the data. So that's what our approach, and we have been deep in conversation with FDA. As a matter of fact, both for blood glucose for our indication and for blood pressure, FDA has recommended us to take the de novo route, which is the novel device route. The the onus of that is that you are literally trailblazing a new path for the regulatory path. But the advantage is you work with FDA, you define the special controls, you define a new product code for regulation. So, which is we feel within our forte because we are scientists, we know how to define these statistical metrics, which are, you know, the statistical metrics that have been defined for the discrete data point devices have to be morphed to take into account the longitudinality of the data and the advantage it delivers. So, what are the new bounds that are clinically acceptable? The clinical community wades into it. From statistics point of view, we also wade into it, and then we define those. So that's how we are driving our project, working with FDA on defining the special controls both for glucose and blood pressure. Right now, we are in a 200 patient study at Mayo Clinic where we are switching from our current algorithm compares against cuff. And as you know, cuff is also a little bit deviated from the invasive arterial line, which is considered the clinical gold standard. So right now we are in a study in Mayo Clinic, 200 patients. We are collecting data of our restored PPG photoplethysmogram against the invasive arterial line waveform. And we are moving further accurate, closer to the actual arterial line blood pressure. And we also published our initial results in two leading conferences on diabetes and hypertension. Now we are looking into our first journal publication. And that's basically on the accuracy side. That's our overall comment that we are very deep into clinical studies, reporting results, and moving forward. With FDA, we already crossed the pre-submission stage, and that's how we got their guidance recommendation, and we started working with them closely on defining the new product code for these two parameters, and we are expecting the submission to FDA by first quarter next year. So we can keep our fingers crossed and knock on wood. We can tell you by second half of next year we will have a class 2 regulated, truly non-invasive continuous device, multifunction device, which is glucose and blood pressure. FDA also asked us to report the accuracy of heart rate, which they don't for other wearables like the Apple Watch or Fitbit or Samsung. FDA applied their the discretionary oversight that as long as you use it for wellness purposes, you don't need to report clinical studies. But for us, they asked us to report the heart rate accuracy also because it's used in medical purpose. So that's what we have been taking forward, and that's our accuracy approach. Now, I'll stop for a minute if you have any kind of question on the accuracy side before I go to the business side.
No, other than, and this ties into the business, of course, if you produce, you're producing a continuous monitoring non-invasive system, addressing areas that are not widely addressed yet. You're doing it so it's really a health-related device rather than pure consumer. Then the question, and it's related to the business side, is if it's a $10,000 device, then you might as well just use traditional technique. If even though you have the advantages, it's non-invasive and it's continuous monitoring. So I guess price point is also, and the ease in which you can scale this and manufacture it at a low price point, right? So
exactly, you are darn right. That's exactly the path we have been choosing. And we are always aware of Apple or any other big consumer tech's potential presence in the coming months and years in this space. And this is a serious enough problem. We fully appreciate the fact that the big consumer tech companies will be looking into these problems with the proper seriousness, and they will be delivering a very good solution. but this market is big enough, Stephen, that we can coexist with Apple or Samsung or Fitbit or a product from Amazon, whoever it is, primarily because of this price point question that you raised. Because the consumer tech, the top products, they will operate in a prime kind of price point, whereas as a smaller company and for a targeted audience, we can operate at a lower price point, keeping a smaller gross margin with respect to our cogs, and we can still survive as a small company very well. We don't really need to get into like $500,000 device that it becomes kind of a serious problem from the price point of view.
I see. So it's an interesting company that you've created, and I can see the utility of what you're mentioning and the continuous monitoring, and it's non-invasive. I mean, and those are great value points, and you're trying to set a price point that's competitive with some of the big tech companies as they are also addressing this area. Or I'm assuming they're addressing this area because they look at things years in advance, right? So
Right.
Apple would be, or Samsung would be two of your main competitors on the consumer side.
Yes.
Okay. So that's really fascinating.
I actually wanted to add one more comment on this, is that as far as the scalability of the business, we can either think of a medtech company doing a white label on our product. I'm giving some names. For example, it could be Medtronic or Abbott or Dexcom or Roche or LifeScan. One of them can do white label and take it through their channels, because as a established medtech, they have the entire army to take it to the end users. That's one route, and they will have their own price points, and they will coexist with the consumer product if they take it as a white label approach. Alternatively, if you think about the consumer white label, the consumer tech, if once we get past FDA and once we prove our hardcore performance metrics of our algorithms, because we use a market existing sensor, so no innovation on the sensor. Although we have our own 12 patents how to extend this sensor to do even better, but with the current device, we use a market existing sensor. So all our IPs in algorithms, so we can, once we prove our quality metrics, these big companies may also be interested in doing a license royalty based play with our algorithms on their device, and we are absolutely open to those conversations as well.
I see. So what you're saying then is the hardware is sort of readily available, and your differentiation is the algorithms that you layering in on top of the hardware. And then in that case, then in some ways, the hardware, you could be agnostic of what the hardware is, right? Because it's really the proprietary part is in your algorithms.
Yes.
And of course, once it's algorithm based, then it's easier to scale, right? So
Yes.
it's the application of the algorithm across multiple devices. That's interesting. And then even that philosophy that's embedded in your algorithms could be applied to other areas perhaps as well.
Correct.
So let's switch gears then. So you talked about how you got into this field, your work with Intel and others, and you're interested in chip technology and sensor technology driven from your experiences within your family. And then you founded a company and you're trying to differentiate that company and so on. Let's get into the future of the marketplace. Where do you see artificial intelligence and algorithms going? What are your views on generative AI, in particular, not the synthetic data part of it, but on the large language models or large foundation models? Where do you see that going? And then I'll stop there, and then I'll ask some more questions. For example, where do you think chips are going? Oh, why don't we add that too? So where are algorithms going? Where is AI, machine learning going? And where are chip technology? Where do you see that going in 2 to 3 years?
Absolutely. And if you don't mind, Stephen, I mean, algorithms and the advance of AI is a very broad topic, and I want to restrict myself only within the space of healthcare delivery, because that's the space that I have been very closely associated with for last several years, and understand that better than I do in other applications of AI. So I would talk about a couple of things here. First of all, I personally feel it's a great power that we have got over the last couple of decades, and the power is really in the process of being unleashed. The power has not fully been utilized in the healthcare space yet. It's just starting, honestly. We are in the nascent phase of the application of AI in all possible areas, including healthcare. And what particularly I felt that has a tremendous potential is that the medical doctors have all the knowledge that you need to properly treat an individual with an illness. What they lack and what they have been traditionally lacking is data and some easy see more data. Also, if someone has to manually look into the data, that takes all their time. So essentially, longitudinal data and its quick interpretation and presentation to accurate interpretation and presentation to the doctor is going to tremendously help a doctor. Just giving a simple example from my own context, from my product's context. Today, the general expectation, if you are a, let's say if you are a pre-diabetic or an early stage diabetic, is that you will do an A1C blood test every 3 months. And your doctor will look at your blood test in January, again in April, and they will decide what is the medication dose that they're going to give it to you. But what they're really missing is what's happening in the 3 months between the January and April. And if they have a lot of data and its simple interpretation presented to them at the time you are walking into the clinic next time, they can much further titrate that medication dose. You can do much better with that dosing. One aspect is your own lifestyle changes that AI will start recommending from cloud with this data. Second aspect is that the further titration of the medication. These two things combined will deliver you a much longer, happier, healthier life than what we are experiencing today as the patients. That is one aspect. Then another aspect is when you talk about the generative AI and large language models, the recent conferences on the healthcare field, different conferences that I attended, I saw a tremendous exuberance within the healthcare community, the doctors, because what used to take them a substantial part of their daily routine, like taking notes, interpreting, and basically getting it to the clinical decision making point, is largely getting covered by the large language models. Like many other spaces in healthcare, this is going to really transform most of the time consuming, wasted, and mundane stuff to the blink of your eye. And that's going to open up the time for the doctors as well as the support staffs, and they are going to do much more ingrained, delivering the healthcare and the treatment and care to the individual, because they don't need to work about this taking notes, processing, all those things. There are many other aspects of generative AI that we could get into, but in the interest of time, I'm going to shorten it now. The second question you had is that what the chips are going. Um, the chips are getting just like what we saw with the mobile revolution, that ARM core based approach came compared to the traditional CISC approach that Intel had. Now with the advent of AI, the you know the architectural style that is particularly suitable for AI computation is really advancing very quickly, rapidly. And the next movements of that architectural style changes started with the server side first. So the cloud servers were becoming more and more AI savvy, AI focused, thanks to Nvidia and other companies. But now the next movement has started, that a wearable processor, how can it host edge AI computation on the device? Because in the first generation of the IoT devices, the sensor data was collecting at the field, but was taken raw to the cloud, and all AI was happening in cloud, and the interpretation was coming back to you. In the next generation, in the generation that we are in now, and it's proliferating, the AI will happen on the IoT device itself. So on the healthcare space, we do our deep learning for the glucose or blood pressure right on the device. And this chip is not really the best chip for doing that. But I see that new chips are coming from some startups that are much more focused on AI based computation, even completely new technology like magnetic memory and in memory computation that's happening, which is very conducive for the AI type of computational tasks. So a tremendous amount of research and innovation and productization has been happening on edge computation on IoT devices, and that's going to proliferate like any other field into the healthcare field, and will really transform the way we live our life. Honestly, I'm extremely bullish about that.
So let me just summarize what I hear you're saying. You're saying on the algorithm side, because of this continuous data flow and the ability to analyze it, you're getting very accurate or more precise precision and personalized medicine, basically. And the fact that you could manage the medication much better because of this continuous data flow, which is being created by these or produced by these non-invasive continuous monitoring wearable devices. So that's helping really on the algorithmic side. Also on the algorithmic side, saying that in the healthcare field, there's a lot of excitement now in the possibilities of doing the note-taking and and assisting as a companion, as a co-pilot in essence, on the analysis when doctors are meeting with patients and then looking at what are sort of the possible diagnostic aspects, but really the doctor's still overseeing it all heavily integrated, but it can save time, right? And then on the chip side, you're saying, particularly on the edge computing, edge being, you don't have to be connected to the cloud. You can have the processor matched at the sensor on the wearable somewhere out there on a mobile basis and not having to communicate with the cloud and that processing occurring. And because advances in chip technology, for example, 3D chip architecture or RRAM, resistive RAM, integrated and high bandwidth with the CPU, but that could be in a edge chip device. And a lot of these kind of systems on a chip complexes that are coming out there, but that can be put into a wearable. All of that is an accelerating and producing a lot of positive outcomes. Did I miss anything? And I just kind of
No,
summarize what I'm hearing.
no, this was a great summary of what I said. Absolutely. So lot of new topics to be very bullish on where we are right now.
Okay, so now let's get into maybe on the philosophical side. There's this idea that the integration of new chip technologies, even neuromorphic chip technologies, 3D chip architectures, and that's driving a lot of what's happening out there. And then you have this really rapid revolution occurring with large foundation models. Do you think then that we'll be getting into more AGI or artificial general intelligence, where it's not human, but it's comparable in many respects and maybe will even exceed some of the things we can do. And that will be like a parallel kind of evolution occurring on the machine side. Where do you see that going?
I think that is the next extension of the research, where basically we the automation and decision making and intelligence is getting to a point that that so the human mind always kind of starts thinking about what next, and basically as a natural tendency we are also thinking how we can build a machine that can literally think like a human and make decisions on the go, and considering many different signals, many noise factors, confounding factors. And I think that research will continue. Of course, there is a philosophical angle to it, that how much power will we give to machine. I mean, there's a age old dichotomy and a debate that whether we would ever let machines become compatible in their intelligence to us, and will that cause some real kind of you know, like worrisome situations. So I think at that level, the research will continue, but at that, when it gets closer to a machine intelligence getting parallel to human intelligence, I think it will not be in the hand of the scientists. It will be in the hand of the government and the regulatory bodies, and the policy making will happen at the government level, at the maybe at the international governance level, and that's where ultimately it will be kind of guided and controlled and kind of carved out. But researchers like us will always explore new possibilities.
I did a two-part interview with Philip Wong. He's at Stanford. In fact, he won an IEEE award for his work in semiconductors. And he was on sabbatical where he was chief scientist for Taiwan Semiconductor
Mm.
and continues as chief scientist as an advisor. And he talked about a meeting certain kind of by chance with a doctor, and this idea of being able to have a chip within a cell.
Hmm.
And because really the scaling of chips is so small today, it can exist within a cell, and then in real time doing monitoring and maybe even being able to help that cell in some way and do it wirelessly. And that's kind of like has this almost element of science fiction, and yet he's working on this now. So do you see this evolution of, because you're a semiconductor expert, do you see evolution of this sort of nano-chip technologies, even robots in our nano robots in our bodies, and they're seamlessly exist with us, and maybe through some thermal mechanism they can be self-powered in some way? Um,
Absolutely.
and do you
I,
see that
I
in the near term or long term, or where do you
No,
see?
no. I think the research has already started, as you mentioned about Dr. Ong already. Uh, I think the research is already undergoing. I envision the timeline to be at least 10 years to get there. That you have a self-powered nano robot that pretty much kind of can stay within your cell, and these things can do really wonder, because literally one could extrapolate the application of such a nano robotic chip in curing cancer, something like that, right? Deep, they can even repair a rogue DNA which is at the root of a cancer proliferation. So these type of applications are really welcoming, and this will happen. May take 10 years. That's my own kind of a timeline. I would be happier to see it happening within 5 years. But so an interesting connection between the last topic we discussed and this one. I think, when it comes to we as human race developing the technology and innovation and science, this is how we should guide ourselves. For example, personally, I think we should not make a chip which is as intelligent as a human and can really act against human. Rather, we should advance as much as possible, which can be still under the control of a human being, but can go at the even at the cell level, at the molecular level, and do its job, and do its job so well that it couldn't even be thought possible like 10 years or 20 years ago. And one example that comes to my mind on an application, I recently met a top scientist from University of Pittsburgh, who is also in our advisory board, Dr. Sen. He is a regenerative medicine expert, and what he does is he has developed an innovative technology, a cell that you can implant on a wound site, and that will regenerate the cells in that wound site, and it will repair the wound site. So a close connection to, and this is actually an electronics technology. This is a chip. This is almost a molecular chip that he imparts into the wound site and repair that wound site. So these type of applications will really work well. This is where we are headed. It will repair cancer cells, it will repair DNA, it will repair wound sites, it will do wonder in the next 10 to 15 to 20 years for the treatment of human diseases.
So it sounds like we're heading towards a remarkable inflection point in humankind. And because innovation is happening so rapidly today, do you think that we can even forecast 20 years out now? Because of quantum computing, the evolution in chips, the evolution in biotechnology and algorithms and so on. It's just, if you look at the papers that are dropping, even on the large foundation models, large language models, diffusion models, they're like just continuous flow, right?
Absolutely.
And you even see the big tech leaders when they're interviewed, they're saying it's just mind-boggling in essence. I mean, that's my word for it, but
Yes.
of all of the innovation that's occurring. So do you think you can even predict what it's going to be like 10 years from now?
No, it will be very hard to predict for anyone sitting today, even the best scientists of our country, because it is proliferating and growing at a rate that it is beyond anyone's imagination at this moment. But one thing we can say for sure, next 20 years, the computing science and electronics industry and in technology will see wonders in every aspect of human life, and that will transform the way we live today. In next 20 years, it will literally transform the way we live. And I think, one other aspect that I forgot mentioning. So there is this AI, LLM, all these aspects. There is also this many decades, even like century old theoretical question in computer science, when the P will become equal to NP, right? And will it ever become? Uh, I think some of the latest computing paradigms and computing architectures and new technology has been driven toward that as well. And when that happens, I'm actually bullish. I predict that computing architecture wise, we will get to a point in next 20 years maybe, that we'll see a P equal to NP situation. And then all those computations that in our theory of computation book that we considered NP and not solvable in deterministic time will be solved. And that will cause another explosion in our advancement. And I see that that's coming, that's nearing. So I'm totally bullish about that possibility as well.
Right. So maybe for the audience, not all audience members are mathematicians or computer scientists or engineers, and they may not know what you mean by P and NP and so on. So can you define what that means?
Yes, of course. So there are two classes of algorithms. One is called the P or polynomial class of algorithms, and the other is called the non-deterministic polynomial class. And what these two classes mean is that for the polynomial classes of algorithms, you can solve that problem in polynomial time. And for the non-deterministic polynomial class of algorithms or NP class of algorithms, you cannot deterministically solve that problem in polynomial time. So so far the theory is that P and NP are two different classes. They're not same class, and that's why once an algorithm gets defined and puts in the bucket of NP, becomes immediately becomes an object of immense interest to the computer scientists. That how can I solve that in quicker and quicker time? But still, it's non-deterministic polynomial. To give an example, let's say if you have been given, um, you know, let's say I tell you that I give you 5 letters A, B, C, and D and E, right? And I have a specific combination of those letters in my mind. And I ask you that, can you tell me out of these 5 letters A, B, C, D, and E, what is the combination that I have in my mind? Can you answer that? You cannot answer that theoretically in polynomial time, because you have to consider all combinations, and one of them will be matching with my own answer. So this is a simple example of a non-deterministic polynomial algorithm. So this type of algorithms will be only solved when there is a computer architecture which is evaluating all the combinations at the same instant of time in parallel. and getting to the answer. That kind of machine doesn't exist today. But I think we are heading toward those type of machines which will really make it like near polynomial time, and then we'll have a solution, and that will cause wonder by itself, because there are so many fundamental problems that sit in the bucket of the non-deterministic polynomial class. They will be solved in polynomial time.
So now let's look at possible approaches to this. So are you talking about electron spin in semiconductor technology, where you can maybe get entanglement and superposition occurring? Are you talking about quantum information science, the technology of quantum
Both of them.
computing? Are you talking about really sort of the rare breed of deep learning and sort of the continuation on the algorithm side, where maybe these large language models are so massive we don't even know what's going on, but they're evaluating billions of things at the same time, right? More than a human being can do. And
Yes.
it's uncovering things that we just could not even conceive of when they're applied to different problems. Are you talking about those as examples? And then can you go a little bit deeper what that
I would do a little bit deeper, and that's a great question that you raised. And this is my philosophical answer. Algorithms will keep on advancing, will keep on making the computational time shorter and shorter. But algorithm cannot alone solve the P equal to NP question. Philosophically, algorithms can never alone solve that. Only a new fabric, a new paradigm, basically from the hardware perspective, can solve that problem. Because if algorithms could alone solve it, then this problem would have been solved years ago. Theoretically, classically, these are two different buckets. Just algorithms cannot solve these two, and cannot combine these two buckets together. There can be a physical innovation uh, in building a physical system that can make these two classes come almost close to each other, almost overlap to each other. So yes, algorithms will advance like LLM and everything. But end of the day, you need something like an electronic spin or quantum computing or all these the completely new orthogonal computing paradigms, computing architectures that are coming. Those will have the potential to ultimately bridge the gap.
And then we've both alluded to quantum computing, and really the sort of the foundation of quantum computing is parallelism, right? Through superposition and entanglement, it can work on multiple
That's exactly what
paths
it
at the same time, right? So
and that was the reason that why quantum computing or electron spin, those kind of mechanisms have been picked up and are getting explored, because we need tremendous amount of parallel computing, parallelly evaluating different choices, so that you can get to the best choice at the same output point, not in sequence. Because once you think of sequence, then all bet is off. You have to do it in parallel.
yeah, and I guess the famous problem would be the traveling salesman problem, right?
Yes,
You got a traveling salesman visiting 200 cities. What's the optimum path? And you can't do that on a classical computer.
absolutely
It's,
not.
it's
And
not
people
possible.
have, yes, in computer science, we have dealt with that problem so many times, even in circuitry, even in designing an electronic circuit with the minimal number of layer overlaps and stuff. It's the same, another variant of the TSP, the traveling salesman problem. And we have come up with very good heuristics, very good kind of close to polynomial approximations, but we have never hit a polynomial solution. It's not possible with the current computing architecture. We have to get to the next computing architecture which will solve that in parallel, in polynomial time.
Yeah, and I guess there's this whole idea of quantum inspired algorithms, right? So quantum computing people solve some kind of or show some promise, and then the algorithmic side says, "Well, we'll use a quantum inspired algorithm runs on classic computers, and guess what? We can actually solve that in polynomial time, right?"
Yes,
Oh,
yes, that's, and I tell you, Stephen, once that happens, and I'm expecting that in next 10 years, 10 to 15 years at most, this is gonna open up. This is going to create a riot in computer science
Yeah,
because the problems that are considered to be hard and not solvable in polynomial time will all be solved, and we'll see a very different world. I mean, so many mm, hundreds of thousands of applications of those NP problems will come out
right.
in different spaces, and every single one of them will probably create a startup of its own.
That's, that's true.
so we are literally stepping into a very bullish time for computer science in general in our lifetime.
Even on the classical computing side, we have exascale computing, and it was thought at one time exascale wasn't even possible. And in fact, if you watch the old Star Trek shows, you have data, and some of those shows, data actually quantified the amount of calculation this android could do. Well, actually, our computers are actually could do more now.
Absolutely, absolutely. In fact, I would allude to the my own problem that we have been working on in this startup. There's non-invasive measurement of glucose or prediction of glucose. We call prediction because we use deep learning. There have been so many failed efforts in the last 25 years, and people often come to me and say that there are so many failures. Why are you still working on it? I said that's what in every single field. That's how we have advanced.
Right.
Every single field has advanced through a long history of failure, and still people haven't given up. And that's why we have got a solution in every single space. So
Yeah, it's
yeah,
like AI and all of the winters that the AI has gone through. Right.
that's true. That's true. That's true. And a tremendous advancement has happened on the capability of the sensor, the miniaturization of the technology,
Right.
then on the computing side, right? I mean, a lot of noise that was not filterable before now are filterable. And then the power of AI is really getting unleashed on very noisy, very low SNR data. We deal with very low signal to noise ratio data all the time, which was not there. People didn't even know how to deal with that low SNR. Tell you, frankly, we deal with the data where we have only 0.1% glucose information.
Right.
That kind of low signal to noise ratio data was not even, people couldn't even think of dealing with that data and come up with certain reasonable accuracy, reasonable performance, because it's not just possible. But today we are getting there. It's getting possible, and the community will advance further in the next 5 years. So it's all possible. We are heading in the very right direction in every single aspect of computer science.
Yeah, there is no or there is no no. It's a yes with conditions,
Absolutely, absolutely.
which you
And
can
even
put
if
them.
it's not possible today, the scientific community shouldn't give up in pursuit of trying to solve that problem.
So Alodeep, we explored a lot of different areas, and it's just a fascinating time we live in. And this is to our final question. What's your recommendations to our audience?
My recommendation, I think, because we are all part of a very coherent science-focused community, and what I was just alluding to in the last minute is that we should never give up on the face of a hard problem.
Mhm.
We should look into the problem. Our scientific mind will be put together to figure out what are the current obstacles, how to eliminate one obstacle at a time, and still keep our focus towards solving that problem. That's how we have advanced over the last 100, 200, 300 years, and our race will advance, keep on advancing that way.
Yeah, and I guess then living in the boundary layers, right? Stretch goals, stepwise incremental refinement,
Absolutely.
and that's how you create innovation and invention, right? So,
Absolutely,
yeah.
absolutely. I just to think of one quick topic, like how innovative people are. Like about 10, 12 years back, when I was considering a postdoctoral position after my PhD, there was once a very well-known professor from Purdue. He was looking at a new paradigm called imprecise computing, which is so paradoxical to even think of, right? Would you ever think of doing computing imprecisely? We're never taught in school for that, right? But that whole area opened up because he found out a very constrained computing medium where the full potential, full power of computation is not possible. And that led him to thinking that how much precision I can lose and I can still attain the near perfect target. And that led to imprecise computing. So that's exactly, I mean, in response to your last comment, that the human mind has always found how to navigate through very difficult path and still come closer and closer to a solution.
Yeah, and I guess that speaks to this idea of grit, perseverance and having some optimism as well, right? So, especially during these interesting times we live in right now. So,
Yes.
Alodeep, thank you for coming in and sharing so many of your deep insights with our audience.
Thank you very much for having me, and it's my honor to have this interaction with you.
Thank you for listening to the Brand Called You videocast and podcast, a platform that brings you knowledge, experience, and wisdom of hundreds of successful individuals from around the world. Do visit our website www.tbcy.in to watch and listen to the stories of many more individuals. You can also follow us on YouTube, Facebook, Instagram, and Twitter. Just search for the Brand Called You.